We have been using the idea of congruence already, but in a casual and unsystematic way. In grade 8, we introduced and experimented with concepts around congruence through physical models, transparencies, or geometry software like GeoGebra or Desmos. Specifically, we had to 1. Understand that a two-dimensional or flat figure is congruent to another if the second can be obtained from the first by a sequence of rigid motions. Remember? Rotations, reflections, and translations. Then 2, describe a sequence that exhibits the congruence between the two congruent figures. How do we map one onto another? As with so many other concepts in high school geometry, congruence is familiar, but now we study it with greater precision and focus on the language with which we discuss it. Let us recall some facts related to congruence that appeared previously in this unit. First, we observed that rotations, translations, and reflections, and thus all rigid motions, preserve the lengths of segments and the measures of angles. We think of two segments, respectively angles, as the same in an important respect if they have the same length, respectively degree measure, and thus sameness of these objects relating to measure is well characterized by the existence of a rigid motion mapping one thing to another. Defining congruence by means of rigid motion extends this notion of sameness to arbitrary figures. That means anything, any figure, while clarifying the meaning in an articulate or specific way. 2. We noted that a symmetry is a rigid motion that carries a figure to itself. So, how do these facts about rigid motions and symmetry relate to congruence? We define two figures in the plane as congruent if there exists a finite or specific composition of basic rigid motions that maps one figure onto the other. It might seem easy to equate two figures being congruent to having the same size and same shape. A lot of times when we say two figures are congruent, that's what we mean. I know that I have said it repeatedly in class before. The phrase same size and same shape has intuitive meaning and helps to paint a mental picture. But it is not a definition. As in a court of law, to establish guilt is not enough to point out that the defendant looks like a sneaky, unsavory type. We need to point to exact pieces of evidence concerning the specific charges. It is also not enough that the defendant did something bad. It must be a violation of a specific law. Same size and same shape is on the level of, he looks like a sneaky bad guy who deserves to be in jail. And we know that that wouldn't work. It is also not enough to say that they are alike in all respects except position in the plane. I know I've said that one before too. We are saying that there is some particular rigid motion that carries one to another. Almost always, when we use congruence in an explanation proof, we need to refer to the rigid motion. To show that two figures are congruent, we only need to show that there is a transformation that maps one directly onto the other. However, once we know that there is a transformation, then we know that there are actually many such transformations, and it can be useful to consider more than one. We see this when discussing the symmetries of a figure. A symmetry is nothing other than a congruence of an object with itself. So when we looked at the square, we saw that it had 8 different symmetries. 4 ways that it could be rotated to land back on top of itself, and then 4 ways that could be reflected over a line back on top of itself. A figure may have many different rigid motions that map it onto itself. When we talked about the equilateral triangle, if it had, say, a side length of 1, there are 6 different rigid motions that will map it to itself. Whenever this occurs, it is because of a symmetry in the objects being compared. Lastly, we discuss the relationship between congruence and correspondence. A correspondence between two figures is a function from the parts of one figure to the parts of the other, with no requirements concerning same measure or existence of rigid motions. If we have a rigid motion, t, that takes one figure to another, then we have a correspondence between the parts, meaning whereas typically we would say point A becomes A prime. We would say that those 2 points correspond, and so do all the other parts in the 2 shapes. For example, if the first figure contains segment AB, then the second includes a corresponding segment T of A and T of B. The transformations of those points after, like the locations of those points after the transformation, so that means those 2 segments correspond. But listen to this. We do not need to have congruence in order to have correspondence. We'll talk more about that later in detail when we get to dilations. But for now, just consider that we might list the parts of one figure and pair them with the parts of another. With 2 triangles, we might match vertex to vertex. Then the sides and angles in the first have corresponding parts in the second. But being able to set up a correspondence like this does not mean that there is rigid motion that produces it. The sides of the first might be paired with the sides of different length in the second. Correspondence in this sense is important in triangle similarity. You'll learn more about that when we talk about dilations.